Lie still now and let the day fall away. The weight of your body is settling into the surface beneath you, and the small noises of the house are fading into a soft, distant hum. Outside, the world has turned away from the light, and your room has become a quiet, dark harbor. In this stillness, there is nothing you need to do, nothing you need to solve, and nothing you need to remember. There is only the dark and the quiet and the slow, steady rhythm of your own breath, moving in and out like a gentle tide. And as you rest here, adrift between waking and sleep, I want to turn your thoughts towards something that has been with you for every single day of your life, something so constant and so faithful that it is easy to forget just how remarkable it truly is. I want to speak, very softly and very slowly, about the star that lights our days and makes all of life possible. I want to tell you about the sun. Think of it now, not as a blazing disk that hurts your eyes to look at, but as a steady, quiet presence. A warm, golden constant that has risen and set more than 1 trillion times since the earth was young. Every morning of your life it has been there, slipping above the horizon to paint the sky in soft pinks and pale oranges. Every evening it has slipped away again, drawing a blanket of darkness over your part of the world so that you could rest. It is the most familiar object in all of human experience, the one great certainty in the sky. And right now, while you lie here in the cool dark, it is still there, shining on the other side of the world, warming some far-off ocean, lighting some distant mountainside. Its light is falling on forests and deserts, and the wide, rolling plains of the sea. It never stops. It has never stopped. For billions of years, it has been pouring out its light in every direction, and a tiny, precious fraction of that light has been traveling the 93 million miles between the sun and our small planet to find you here, every day of your life. That distance, 93 million miles, is a number so large that it can be hard to feel its meaning. So let us slow it down and make it gentle. Imagine, for a moment, that you could drive a car straight up into the sky, heading toward the sun at a steady highway speed of 60 miles per hour. If you never stopped for gas, never slowed down, and never rested, it would take you nearly 180 years just to cross that distance. 180 years of driving, just to reach the star that warms your face on a summer afternoon. That is how far away it is. And yet, even from that immense distance, it fills our days with light so bright that the whole sky turns blue, and it fills our world with enough warmth to melt snow, to grow forests, to raise the oceans into clouds, and bring them back down as rain. That quiet, distant star is the engine of everything we see and feel on the surface of the earth, and it does all of this without a sound, without a flicker, without ever asking for anything in return. The sun, in the simplest and truest terms, is the closest star to the earth. When you look up on a clear night and see all those tiny points of light scattered across the dark, you are seeing other suns, other stars, each one burning in its own distant corner of the galaxy. But they are so far away that their light is only a faint, cold glimmer by the time it reaches your eyes. The sun is different. The sun is our star, close enough to flood our sky with daylight, close enough to feel on your skin. It is a star, just like all the others, a giant ball of glowing gas, and it is sitting right on our cosmic doorstep. The next nearest star, a star named Proxima Centauri, is something like 25 trillion miles away, so far that its light takes more than 4 years to cross the gap. The sun's light reaches us in about 8 minutes. That is how close it is, relatively speaking, in the vast, quiet reaches of space. It is our star, the anchor of our sky, the hearth fire around which our little planetary family has gathered since the beginning. As you lie here, letting these words wash over you, I want to give you a simple, calming promise about what is to come. In the minutes ahead, we are going to take a slow, unhurried walk through the life of this star. We are not going to rush, and we are not going to fill your mind with complicated facts that you need to hold on to. There will be no test at the end, nothing you have to memorize or recall. Think of this instead as a quiet, drifting journey, like floating on a slow-moving river under a sky full of stars. I will tell you what the sun is made of, and how it makes its light, and how that light travels all the way out from its deep interior to the surface and then across space to the earth. I will tell you about the sun's quiet, slow rhythms, the patterns on its surface, and the soft, invisible wind it sends out past every planet. I will tell you how it began, billions of years ago, and how it will slowly, gently change in the billions of years yet to come. But none of this is information you need to grasp tightly. You can let it drift over you like a warm breeze, and if a thought slips away before you can hold it, that is perfectly fine. It will come around again, or it won't, and either way, you are exactly where you need to be. The story of the sun is, in many ways, a story of stillness within motion. From our place here on Earth, the sun appears to move across our sky each day, rising in the east and setting in the west. But you know, deep in your quiet mind, that this motion is really our own. The Earth is spinning, slowly and steadily, turning us toward the sun each morning and away from it each night. The sun, in its own deep reality, sits at the center, holding still while we dance around it. There is something deeply restful in that thought. While we spin and orbit and go about our busy lives, the sun remains, a fixed and steady center, a point of calm around which everything else turns. It is the great stillness at the heart of our solar system, and its gravity, its quiet, invisible pull, keeps everything in its place. The Earth, the other planets, the asteroids, the comets, all of them tracing their slow, predictable paths around that one steady point of light and warmth. So as you settle deeper into your pillow, as your breathing slows and your thoughts begin to soften at the edges, I invite you to hold this one simple image in your mind, a single star, glowing softly in the vast dark of space, with a family of small worlds circling quietly around it. And on one of those small worlds, a world of blue oceans and white clouds and green, growing things, there is you, lying in the dark, listening to the story of that star. You are connected to it, right now, by the light that left its surface 8 minutes ago and traveled all that way to slip gently through your window blinds and rest, unseen, on your bedroom wall. You are connected to it by the warmth that seeps into your room even on the coldest days, a distant echo of the immense heat at the sun's heart. And you are connected to it by the very atoms in your body, atoms that were forged in stars long before our sun was even born. That is a story for another time, a deeper drift into the past, but for now, just let the thoughts settle around you like a soft blanket. You are part of this great, slow, beautiful system, and right now, there is nothing required of you but to rest and to listen. The sun, at this very moment, is shining. It is shining on the far side of the world, where people are going about their morning routines, making coffee, walking dogs, opening curtains to let the day in. It is shining on the middle of the Pacific Ocean, where the water stretches out in all directions, empty and blue and utterly peaceful. It is shining on the peaks of mountains that no human eye has ever seen, and on the leaves of ancient forests where the only sounds are birdsong and the rustle of wind. It is shining, in short, on a world of extraordinary beauty and variety, all of it powered by that one distant star. And here, on your side of the world, it is night. The sun has slipped out of view, and the earth has wrapped you in its shadow, giving you this quiet time to rest and to heal, and to simply be. There is a deep, ancient rhythm to this, a rhythm that every living thing on earth has followed since life first began. The light comes, and the light goes, and in the darkness, the world rests. You are resting now too, and that is exactly as it should be. As we begin this slow walk through the story of the sun, I want you to know that there is no hurry. We will take each idea and turn it over gently, like a smooth stone found on a beach, feeling its weight and its shape before setting it down and picking up the next. If your mind wanders, let it wander. If you drift off to sleep before we reach the end, then these words have done their job, and the story will be here waiting for you whenever you want to return to it. The sun itself is not in a hurry. It has been burning for 4.5 billion years, and it will burn for billions more. It takes its time, moving through its own slow cycles, and we can take our time too. There is something deeply comforting in that, I think. In a world that often feels fast and demanding, the sun is a reminder that the most powerful things in the universe move at their own pace, with a kind of quiet, unhurried grace. You can do the same, right here, right now. You can let your own inner pace slow down to match the steady, ancient rhythm of the star that lights your days. So lie back and let your eyes stay closed, and let the story begin to unfold. Picture, if you can, a vast darkness, a sea of black so deep and so endless that it makes the darkest night you have ever seen seem bright by comparison. And in the center of that darkness, one point of light, not a harsh, glaring light, but a soft, steady, golden glow, like a lamp left burning in a window to guide you home. That is our sun. That is the star that has been with you for every moment of your life, the star that warmed the very first creatures to crawl out of the ancient seas, the star that will still be shining long after everything we know has faded into memory. It is ancient and it is faithful, and it is, in the truest sense, the giver of all life. And now, in the quiet of this night, we are going to get to know it a little better. We are going to travel, very slowly and very gently, from its deep, burning heart out to its surface and beyond, into the soft, invisible halo that surrounds it. And by the end, I hope you will feel, even in the dark of your room, even on the edge of sleep, the quiet, steady warmth of that connection. It is always there. It has never left you. And right now, as you drift, it is shining for you, just as it always has. And so, as you drift deeper into that quiet, comfortable place between waking and sleep, let us begin our slow walk by asking the most basic, most gentle question of all. What is the sun, really? We see it in the sky so often that we rarely stop to think about what it actually is. A bright disk, a source of warmth, a reason to squint when you step outside on a summer afternoon. But what is it made of? What would you find if you could fly close to it, past the orbit of Mercury, past the point where any spacecraft has ever traveled, and look at it with your own eyes? The answer is both wonderfully simple and quietly extraordinary, and we can take our time unfolding it, layer by soft layer, like opening a gift that does not need to be rushed. The first and most important thing to know is this: the sun is a star. It is not a planet, like the Earth or Mars or Jupiter. It is not a solid body that you could ever stand on. And it is not a fire, not in the way we usually use that word. When you light a candle or strike a match or watch a log burn in a fireplace, you are seeing a chemical reaction. The wax or the wood or the match head is combining with oxygen in the air, and that combination releases heat and light. But the sun does not burn that way. There is no oxygen in space around it, and if the sun were simply a giant lump of burning fuel, it would have used itself up long ago, in a cosmic blink of time. The sun is something much more profound, much longer lasting, and much, much stranger than an ordinary fire. It is a giant ball of glowing gas, a sphere so large that it contains almost all of the material in the entire solar system, and it shines for reasons that are hidden deep, deep inside it, in a place we will travel to soon. To get a sense of what the sun is made of, we have to think about the simplest and most common substance in the universe. Most of the sun, about 3/4 of its entire mass, is made of a gas called hydrogen. Hydrogen is the lightest of all the elements, the simplest building block of matter. On Earth, we most often encounter it bound up with oxygen in water, the familiar H2O from school days. But in its pure form, it is an invisible, odorless gas that floats away into the sky if released. The sun is full of it, vast oceans of hydrogen gas, stretching for hundreds of thousands of miles in every direction. The second most common substance in the sun is another light gas called helium, a gas that we use on Earth to fill balloons that float. Together, hydrogen and helium make up almost the entire sun, something like 98% of everything there. The remaining 2% is a scattering of other elements, a thin dusting of carbon and oxygen and iron and other familiar materials. But these are, in the grand scheme of the sun, almost an afterthought. The sun is, at its heart, a simple thing, a vast, luminous sphere of hydrogen and helium, the two lightest and most ancient substances in the universe. Now, when we say the sun is made of gas, we have to be a little careful, because the gas that makes up the sun is not like any gas you have ever encountered on Earth. The inside of the sun is unimaginably hot, so hot that the atoms of hydrogen and helium are torn apart into their most basic pieces. An atom, as you may remember from school, is made of a tiny, dense core called a nucleus, with even tinier particles called electrons whirling around it. In a normal gas, the atoms are whole and complete, bouncing around like tiny, intact balls. But when you heat a gas to extraordinary temperatures, the collisions between atoms become so violent that the electrons are knocked loose and go flying away from their nuclei. The gas becomes a kind of soup, a swirling mix of free, unattached particles, all moving at incredible speeds. This state of matter, this gas so hot that its atoms have come apart, has its own name. It is called plasma. The sun is not just a ball of gas, it is a ball of plasma, a vast glowing sea of charged particles, and nearly all of the visible universe. The stars and the glowing nebulas, and the vast spaces between galaxies, is filled with this same strange ethereal substance. You can think of plasma as a gas that has become so energized, so alive with heat, that it has shed its outer layers and begun to behave in new and complex ways. It carries electric currents. It responds to magnetic fields. It twists and flows and arches in shapes that can be seen from millions of miles away. And the sun, our steady, faithful sun, is made almost entirely of it. Let us sit for a moment with the scale of this thing, because the size of the sun is one of those facts that is easy to say, but very difficult to truly feel. You know the earth, the ground beneath you, the wide continents and the deep oceans. You know how long it takes to fly from one side of the planet to the other, how the horizon stretches out before you when you stand on a beach and look out at the sea. The earth, our home, is about 8,000 miles across, measured through its center from one side to the other. That is a distance so large that it can take a lifetime to fully explore even a small part of it. And yet, if you could take the earth and place it next to the sun, it would be a tiny thing, a small blue marble next to a vast glowing giant. If the sun were hollow, which it is not, you could line up 109 Earths, side by side, across its width. 109 of our worlds, each one with its mountains and valleys and oceans and skies, placed end to span the face of the sun. That is how large it is. In terms of volume, the amount of space it takes up, you could fit about 1.3 million Earths inside the sun and still have room to spare. 1.3 million. It is a number that slides off the mind, because the mind was not built to hold such things. And that is perfectly fine. You do not need to grasp the full weight of that number right now. You can just let it wash over you, a soft wave of scale and proportion, and know that the sun is very, very large, and the earth, our whole world, is very, very small by comparison. And yet, from our small world, from this quiet room where you lie in the dark, the sun looks just about the same size as the moon in our sky, a perfect, gentle coincidence of distance and size that gives us total eclipses and soft, glowing sunsets. There is a kind of poetry in that, a balance of scale that asks nothing of us but to notice it and smile. Because the sun is so large, it contains almost all of the material in the solar system. If you were to gather up every planet, every moon, every asteroid, every comet, every speck of dust and grain of ice drifting in the space between worlds, and place them all on a giant cosmic scale, they would barely register next to the sun. The sun, all by itself, makes up more than 99% of everything in the solar system. Everything else, The gas giants with their swirling storms, the rocky planets with their solid surfaces, the rings of Saturn and the moons of Jupiter, all of it together is less than 1% of the whole. The solar system is not really a collection of planets with a star in the middle. It is a star, one single vast star, with a thin scattering of leftover material circling it at great distances. That puts our place in things into a gentle, humbling perspective. We live on one of those scattered bits, a tiny, rocky sphere orbiting a star that is, in every meaningful sense, the center of everything around it. And that star, that great sphere of plasma, is not a solid object in any way that we would recognize. There is no ground, no crust, no rocky surface that you could land a spacecraft on. If you could fly a ship toward the sun, you would not hit a definite edge or a solid wall. Instead, you would move through gas that grows thicker and hotter, passing through layers of decreasing clarity until you were deep inside a glowing, roiling sea of plasma, crushed by pressures and temperatures that no material we know of could withstand. The sun is a ball of gas all the way down, held together by its own immense gravity, and it is that gravity, that inward pull, that makes everything else about the sun possible. The weight of the outer layers pressing down on the inner layers is what creates the extreme conditions at the core, the conditions that allow the sun to shine. It is a beautifully balanced system, a push and pull between the inward crush of gravity and the outward push of the energy being released deep within. These two forces, gravity and energy, have been locked in a quiet, steady embrace for billions of years. Neither one winning, neither one losing, just holding the sun in a perfect, glowing sphere. As you lie here in the dark, I want you to hold that image gently in your mind, a vast, luminous ball of gas and plasma, mostly hydrogen and helium, so large that it could swallow 1,000,000 Earths, so massive that it holds the entire solar system in its gravitational embrace, and so hot that its atoms are torn apart into a flowing, charged soup. It is not a fire, not a solid body, not a planet. It is a star, a true star, the only one close enough to feel and see in such detail. And it has been burning, quietly and steadily, for almost the entire history of our planet, and long, long before. Every beam of sunlight that ever touched the face of the earth, every warm ray that fell on the backs of the dinosaurs, every shaft of light that filtered through the leaves of the first forests, every sunrise that ever painted the sky pink and gold, all of it came from this same quiet process, this same steady engine, burning faithfully in the deep, cold dark of space. And in the next part of our slow journey, we will begin to drift inward, toward the very center of that engine, to understand exactly how it works, how such an immense and ancient thing can pour out so much light for so very long. But for now, just rest with the simple picture of what the sun actually is. A star, a ball of glowing gas, a sea of plasma, our steady, faithful companion in the vast, quiet dark. Let that thought settle over you, soft as the blanket you lie under, and let your breathing stay slow and deep, because there is so much more to see, and no hurry at all to get there. Now we drift inward, away from the quiet surface of things, down into the deep heart of the sun, where the light itself is born. This is the part of our journey where we ask the central question, the one that sits at the core of everything else we might ever wonder about this star. How does it shine? How does a ball of gas, floating in the cold dark of space, produce enough light to warm a planet 93 million miles away, and keep doing it, day after day, year after year, for billions of years? The answer is hidden in a place we cannot see, a place buried deep beneath the glowing surface, where conditions are so extreme that the ordinary rules of matter begin to bend and shift. And we are going to travel there now, very slowly, very gently, step by step, so that by the time we arrive, you will understand exactly what is happening in that hidden furnace, and you will see why the sun is not a fire in the ordinary sense, but something far quieter, far deeper, and far more patient. To understand how the sun makes its light, We first have to understand where that light comes from. Not the surface, not the bright disk we see in the sky, but a place much deeper inside. The sun, as we have said, is a vast sphere of gas, mostly hydrogen, and all of that gas has weight. The outer layers of the sun press down on the inner layers with a force that is almost impossible to describe in ordinary terms. Imagine the weight of the entire Pacific Ocean pressing down on a single spot on the ocean floor. Now multiply that by a number so large it has no name. That is the kind of pressure we are talking about at the center of the sun. The weight of hundreds of thousands of miles of gas, all of it crushing inward, squeezing the material at the very core to a density more than 150 times the density of water. A single teaspoon of the sun's core material would weigh more than a small mountain on Earth. That is how tightly packed it is. And where there is that much pressure, there is also heat. The two go together, pressure and heat, twin faces of the same deep process. At the very center of the sun, the temperature reaches about 27 million degrees Fahrenheit. 27 million degrees. It is a number that feels almost imaginary, because nothing in our everyday experience can prepare us for it. The hottest fire you could build on Earth, a blowtorch or a furnace melting steel, reaches a few thousand degrees. The surface of the sun, which we will talk about later, is about 10,000 degrees, and that is already hot enough to vaporize any known material in an instant. But the core is more than 2,000 times hotter than even the sun's own surface. It is a realm of such extreme heat and pressure that the atoms themselves cannot hold together in their normal form. The hydrogen atoms, stripped of their electrons, are just bare nuclei, tiny points of matter moving at incredible speeds, colliding with each other over and over again in the dense, swarming heart of the star. Normally, when two hydrogen nuclei approach each other, they repel one another. They both carry a positive electric charge, and like charges push apart, like the north ends of two magnets refusing to touch. This is a fundamental fact of the universe, a kind of built-in barrier that keeps atoms from casually merging together. But in the core of the sun, the temperature and the pressure are so immense that this barrier can be overcome. The nuclei are moving so fast, and the crush of gravity is so intense, that every so often, two hydrogen nuclei are pushed together with enough force to get past their mutual repulsion. And when they get close enough, a new force takes over, a force that only operates at the very smallest distances, a force that pulls them together and binds them into a new, larger nucleus. This process, this joining of small nuclei into a larger one, is the secret of the sun's light. In simple, everyday words, the sun shines because, deep in its core, hydrogen atoms are being pushed together so hard that they stick, combining into helium. This joining releases a small amount of energy, a tiny burst of light and heat that flies away from the site of the collision. Multiply that tiny burst by the uncountable number of collisions happening every second in the vast core of the sun, and you have an energy output so enormous that it lights the entire solar system. This process has a name, a technical term that you may have heard before, and now, having described it in plain words, we can gently place the name on it. It is called nuclear fusion. Nuclear because it involves the nuclei of atoms, their tiny, dense cores. Fusion because it is a fusing, a joining together of smaller pieces into a larger whole. Nuclear fusion. It is a quiet phrase for such a profound thing. The sun is a fusion engine, a natural reactor that has been running steadily for about 4.5 billion years, converting hydrogen into helium at a rate that is difficult to fully grasp. Every second, deep in the core of the sun, about 600 million tons of hydrogen are turned into helium. 600 million tons every single second. And of that enormous amount of hydrogen, a small fraction, about 4 million tons, is converted directly into pure energy, released as the light and heat that eventually streams out into space. 4 million tons of matter turned into energy every second of every minute of every hour for 4.5 billion years. That is the scale of the process we are talking about. And yet, despite this almost unimaginable rate of consumption, the sun is so vast, so unimaginably huge, that it has barely made a dent in its fuel supply. The sun has been doing this, fusing hydrogen into helium, for the entire history of the Earth and long before. When the first single-celled organisms appeared in the ancient oceans, the sun was already burning, just as it does now. When the first plants crept onto the land, when the first dinosaurs walked through the ferns, when the first humans looked up at the sky and wondered what that bright disk was, the sun was quietly, steadily fusing hydrogen in its core, never flickering, never wavering, never rushing. It is about halfway through its supply of hydrogen fuel now, which means it has another several billion years to go before any real change begins to set in. That is the kind of timescale we are dealing with when we talk about stars. They are not in a hurry. They have never needed to be. Let us pause for a moment and think about the beauty of this process, the quiet, steady balance of it all. The sun does not burn in the way a candle burns, consuming its fuel in a quick, bright flare. It does not explode, though the forces inside it are beyond anything we can imagine. Instead, it sits in a state of perfect, self-regulating balance. The inward crush of gravity, trying to collapse the star into a smaller and smaller space, is exactly balanced by the outward push of the energy released by fusion. If the core were to slow down its fusion rate, gravity would win for a moment, squeezing the core tighter, which would make it hotter and denser, which would speed up the fusion rate again. If the core were to speed up too much, the extra energy would push outward, making the core expand slightly, which would cool it down and slow the fusion rate back to normal. It is a feedback loop of extraordinary elegance, a natural thermostat that has kept the sun shining with almost perfect steadiness for nearly the entire age of the Earth. This is why the sun does not flicker or surge or dim in any way that we would notice. It is too perfectly balanced, too deeply stable. It is, in the truest sense, a steady light in the dark, a constant in a universe of change. The light that is made in the core of the sun, the tiny bursts of energy released by each fusion event, begins its life as very high-energy radiation, the kind of light that is invisible to human eyes, called gamma rays. These gamma rays carry an immense amount of energy, and they are born into a world of almost solid density, a sea of tightly packed particles. They do not travel very far before they hit something, a stray electron or a passing nucleus, and when they hit, they are absorbed and then spat out again in a random direction, with slightly less energy than before. This is the beginning of a journey that we will explore more fully in the next part of our story. But for now, it is enough to know that the light made in the core does not just fly straight out into space. It begins a long, slow, wandering path through the dense inner layers of the sun, a path that will take it tens of thousands of years to complete. The sunlight that warms your face on a summer day, the light that is streaming through your window blinds right now on the other side of the world, was made in the core of the sun long before the first human cities were built, long before the first stone tools were carved, long before our species even walked the earth. It has been traveling through the sun's interior for all of recorded history, bouncing and scattering, and slowly, patiently working its way toward the surface. And only now, in this moment, has it finally escaped, crossing the 93 million miles of space in a swift 8-minute dash to find you here, resting in the dark. That image of light so old and so patient is one of the most restful things I know. It puts our own hurried lives into a gentle, softening perspective. The light that touches your skin is ancient, not in years, but in the journey it has taken. It was born in a furnace 27 million degrees hot, and it has spent tens of thousands of years working its way through a dense, glowing sea of plasma, and now, at the end of its long journey, it arrives here, quiet and warm, asking nothing of you but to be received. And you, lying here in the dark, are receiving it, even now, even in the night. The warmth of your blanket, the memory of daylight in the walls of your room, the very air you breathe, all of it is touched by that ancient, patient light. The sun is shining for you, and it has been shining for you since long before you were born, since long before there were any eyes to see it, and it will continue to shine long after all of our stories have been told. So let that thought settle into the quiet space behind your closed eyes. The sun is a fusion engine, a place where hydrogen is pressed into helium at temperatures and pressures beyond our everyday understanding. This process, this quiet, steady joining of small nuclei into larger ones, is what makes the light. It is not a fire, it is not a chemical reaction, it is a slow, patient, deeply balanced dance of gravity and energy, a dance that has been going on for 4.5 billion years and will go on for billions more. And the light that comes from this dance is ancient by the time it reaches you. Light that has traveled through the dense body of the sun for tens of thousands of years before making its swift, silent journey across space to find your face, your hands, the walls of your room. You are connected to the core of the sun right now, by that light, by that warmth, by the simple fact that you exist in a solar system that is powered by this one quiet, steady star. There is nothing to do with this knowledge, nothing to solve or remember. It is just here, a soft truth to hold in the palm of your mind as you drift further down into sleep. And when you are ready, we will follow that light on its long journey outward, through the dense, dark layers of the sun, toward the surface and beyond. But for now, just rest with the warmth of the core, a warmth that began 27 million degrees hot and has traveled across space and time to keep you company in the dark. And now, as promised, we follow the light. We have stood, in our imagination, at the very center of the sun, where hydrogen is pressed into helium at 27 million degrees, and we have felt, in a quiet way, the immense energy released by that joining. But that light, that tiny burst of energy born in the core, does not simply flash out into space in an instant. Its journey has only just begun, and the path it must travel from the core to the surface is one of the most patient and unhurried journeys in all of nature. This is the part of our story where we slow time down, way down, and sit with the quiet, almost unimaginable patience of light making its way through the body of a star. The light that is created in the core of the sun is born as a kind of light called a gamma ray, a packet of energy that vibrates at a frequency far too high for human eyes to see. It is packed with energy, this tiny newborn spark, and it is born into a world of extraordinary density. The material in the core of the sun is not like the air in your room. It is not even like water or rock. It is a thick, heavy soup of particles, packed together so tightly that a single teaspoon of it would weigh more than a mountain. And this means that the newborn light cannot travel very far at all before it slams into something. Not miles, not feet, not even inches. The distance a gamma ray can travel in the core of the sun before hitting a particle and being absorbed is less than the width of a human hair. It takes a single step, a tiny, microscopic step, and then it is swallowed up by an electron or a proton, its energy transferred to that particle for a brief moment before being spat out again in a new, random direction. This happens over and over and over again, trillions of times, in a slow, staggering, drunken walk that has no straight path and no clear destination. This kind of movement, this random bouncing from one particle to the next, has a name. It is called a random walk, and it is one of the most patient processes in the physical world. Imagine a person standing in the middle of a vast, dark forest, so dense with trees that they can only take one step before bumping into a trunk. They take a step in some random direction, bounce off, and step in another random direction, with no memory of where they have been and no plan for where they are going. Sometimes they move forward, sometimes backward, sometimes sideways. Over time, through sheer persistence, they will eventually find their way out of the forest, but it will take an unimaginably long time. The light in the sun is like that wanderer, taking one tiny step after another, in no particular direction, for tens of thousands of years. The exact number varies depending on where the light is born and what path it happens to take, but a common estimate, A number often cited in quiet books about the sun is that it takes somewhere between 100,000 and 200,000 years for a single packet of light to travel from the core to the surface. 100,000 years, more or less, of bouncing and scattering and slowly, patiently, making its way outward. Let us hold that number gently for a moment, because it is a number that can help us feel the true scale of the sun's interior. 100,000 years ago, on Earth, human beings were just beginning to spread out of Africa and into new continents. Mammoths and saber-toothed cats still walked across the frozen steppes. The last ice age had not yet reached its peak. And deep inside the sun, the light that is warming your skin right now, the light that is streaming through your window on the other side of the world, was just beginning its long, slow climb toward the surface. It was born in the core, a tiny spark of energy, and it began its patient, staggering walk through the dense layers above it. It saw nothing, knew nothing, had no purpose except to bounce and scatter and slowly, inevitably, rise. And rise it did, over all the millennia of human history. While the first cities were built in Mesopotamia, the light was still climbing. While the pyramids rose from the Egyptian sands, the light was still climbing. While the first philosophers walked the streets of Athens, while the first astronomers pointed their telescopes at the sky, while the first steam engines began to hum, and the first electric lights began to glow, the light was still climbing. And only now, in this moment, has it finally broken free of the sun's surface and crossed the 93 million miles of space to find you here, resting in the dark. There is something deeply restful in this thought, something that can soften the edges of our own hurry. The light that reaches us is ancient, not in the sense that it was created long ago in some distant past, but in the sense that it has been traveling, patiently and persistently, for longer than human civilization has existed. It is light that was born before written history, before language, before the first cave paintings were drawn by firelight, and it has spent all of that time just working its way through the body of the sun, step by tiny step, never rushing, never faltering, just following the slow, inevitable pull toward the surface and the freedom of open space. When it finally reaches the surface, when it finally breaks free of that dense, glowing sea, everything changes. The last leg of its journey is so swift, so clean and straight, that it almost feels like a release, a long-held breath finally let go. Once the light clears the surface of the sun, it races outward in every direction at the speed of light, which is about 186,000 miles per second. At that speed, it covers the 93 million miles between the sun and the earth in just over 8 minutes. 8 minutes, after a journey of more than 100,000 years. The contrast is almost too beautiful to hold on to, a moment of swift, silent flight after an age of patient wandering. Think about what that means for a moment. The light that left the sun's surface 8 minutes ago is the same light that was born in the core during the last ice age. It spent 100 millennia stumbling through the dense interior, and then, in the time it takes to brew a cup of tea or watch a short stretch of clouds drift across the sky, it crossed the entire void of space and arrived here, on this small blue world, to touch the leaves of a tree or the surface of a lake or the closed eyelids of someone resting in a quiet room. There is a kind of poetry in that, a gentle, unhurried poetry that asks nothing of us but to notice it. The light that warms us is patient light, ancient light, light that has known the deep interior of a star and has finally, after all that time, found its way to us. And as the light makes its way outward, it changes. The gamma rays born in the core are far too energetic, far too high in frequency for human eyes to see. But as they bounce and scatter and lose energy over tens of thousands of years, they gradually shift down into lower and lower frequencies. By the time the light reaches the surface, it has been broken down and spread out into a broad, gentle spectrum of visible light, the soft, warm glow that we see when we look at the sun through safe eyes. The same energy, the same original spark from the core, has simply been stretched and softened by its long journey, emerging at last as the golden light of a summer afternoon, the pale white light of noon, the deep orange and pink light of a sunset slipping below the horizon. All of it, every color and every shade, is the same ancient energy, delivered to us after a journey that began long before we were here to see it. This long journey of light is, in many ways, a story about patience. The universe, at its deepest levels, is not in a hurry. The processes that power the stars, that shape galaxies, that drive the slow evolution of planets and moons, and the delicate chemistry of life, all of them operate on timescales that make a human lifetime seem like the briefest of flickers. And yet here we are, lying in the dark, able to think about these things, able to trace the path of a single photon from the heart of a star to the surface of our own small world. That is a kind of quiet gift, a moment of connection between the very large and the very small, between the ancient and the present, between the star that shines and the mind that wonders. There is no urgency in this story, no rush to the finish. The light itself has shown us that the deepest things take time, and that there is a strange, quiet beauty in the waiting. So as you lie here, letting your breath slow and your body sink deeper into the mattress, I want you to think of that patient light. It is traveling through the sun right now, in this very moment, light that will not emerge for another 100,000 years. Light that will one day fall on a future Earth, on oceans and mountains that have not yet formed, on eyes that have not yet opened. And there is light emerging now, right now, that was born when mammoths walked the Earth. Light that is streaming across space and arriving here, in this quiet moment, to rest on your skin and your blankets and the walls of your room. You are bathed in ancient light, in patient light, in light that has traveled farther and longer than any human journey could ever hope to match. And that light asks nothing of you. It does not need you to understand it, or remember it, or do anything with it. It simply arrives, quiet and warm and faithful, as it has done for billions of years, and as it will do for billions more. Let that be the thought you hold on to now, as we prepare to drift outward ourselves through the layers of the sun, tracing the path that the light has followed. We will move, very slowly, from the core through the dense, radiating zones above it, through the slow, churning convection that marks the sun's outer interior, and finally to the visible surface, the bright disk that we see in the sky. There is a whole geography inside the sun, a structure of layers and zones and boundaries, each one with its own quiet character, and we are going to explore that geography together, one soft step at a time. But for now, just rest with the patience of light. Let your own thoughts become a little more random, a little more wandering, like the photon in the core. There is no straight line you need to follow, no destination you need to reach. You are just drifting, just bouncing gently from one soft thought to the next, and that is exactly as it should be. The light has waited 100,000 years to reach you. You can wait a little longer before sleep takes you. There is no hurry, and there never was. And so, in that same spirit of unhurried drifting, let us now build a simple map of the sun's interior. We have spoken of the core, where the light is born, and we have followed that light on its long, patient journey outward. But the sun is not just a uniform ball of hot gas from center to surface. It has structure, a kind of internal geography, with distinct layers that each behave in their own quiet way. These layers are not solid boundaries, not like the skin of an apple or the shell of an egg. They are gradual transitions, zones where the conditions change slowly from one state to another, and they wrap around each other like the layers of a soft, glowing onion, each one with a character all its own. We are going to travel through them now, moving outward from the core, step by gentle step, so that by the time we reach the visible surface, you will have a clear, calm picture of the architecture of a star. We begin, as we must, at the center. The core of the sun is the innermost region, the furnace where nuclear fusion takes place, and it extends from the very center outward to about 1/4 of the sun's radius, roughly from the center to a point about 107,000 miles out. That may sound like a large distance, and it is, But remember that the Sun as a whole is about 432,000 miles in radius, so the core is a relatively small part of the whole volume. And yet, this small central region contains nearly half of all the mass in the Sun. The density is that extreme, the material packed that tightly together. The core is where the temperature and the pressure reach their peak, 27 million degrees Fahrenheit, and a crush of weight that is almost beyond imagining. This is the engine room, the quiet, hidden place where the Sun's energy is made. Without the core, the rest of the Sun would be a cold, dark ball of gas, drifting invisible through space. But the core is there, burning steadily, and everything else we will talk about flows outward from that one central fact. Moving outward from the core, we enter the next layer, the region that surrounds the core like a thick, dense blanket. This is the zone where the light begins its long, random walk, and it has a name that describes what happens there. It is called the radiative zone, because in this layer, energy moves primarily by radiation, which is just a technical way of saying that the light bounces from particle to particle, being absorbed and re-emitted in a slow, staggering path. The radiative zone stretches from the outer edge of the core, about 1/4 of the way out from the center, to about 70% of the Sun's radius. That is a vast expanse, hundreds of thousands of miles of dense, hot plasma, and it is through this region that the light must make its slow, patient climb. The temperature in the radiative zone drops steadily as you move outward, from the 27 million degrees of the core boundary down to about 2 million degrees at the outer edge. Still unimaginably hot by any earthly measure, but much cooler than the core. The density also drops, from that heavy, almost solid-like crush at the bottom to something still dense but less extreme at the top. The light, born as gamma rays in the core, gradually loses energy as it travels through this zone, shifting down through the spectrum until, by the time it reaches the top of the radiative zone, it has softened into the kind of light we would recognize as X-rays and extreme ultraviolet, still invisible to human eyes, but much closer to the visible light it will eventually become. This journey through the radiative zone is the longest part of the light's travel, the part that takes those tens of thousands of years we spoke about earlier. The material here is so tightly packed that a photon can only travel a fraction of an inch before being absorbed and redirected. It is a realm of almost pure patience, a place where nothing happens quickly, where energy moves with the slow, steady persistence of ice melting in a warm room. You can imagine it as a vast, dim, glowing ocean, silent and deep, where the only movement is the gentle, random drift of light working its way toward the surface. There are no storms here, no turbulence, no sudden shifts. The radiative zone is a place of quiet order, a slow, steady flow of energy from the hot core to the cooler regions above, and the light that passes through it carries with it the only record of what is happening in the core, a message from the center of the Sun that takes tens of thousands of years to be delivered. But as we continue to move outward, the character of the Sun begins to change. About 70% of the way from the center to the surface, we cross a subtle but important boundary. The material here has cooled enough and thinned enough that the steady, orderly flow of radiative energy is no longer the most efficient way to move heat outward. The plasma becomes less transparent, more opaque to radiation, and the heat begins to build up, like water behind a dam. When this happens, the material itself begins to move. Hot plasma from deeper down, carrying its heat with it, rises toward the surface in great slow currents. As it rises, it cools, and once it has released its heat near the surface, it sinks back down again to be reheated and rise once more. This churning, circular motion is very much like what happens when you heat a pot of thick soup on a stove. The soup at the bottom, closest to the heat, becomes warmer and less dense, so it rises. At the surface, it cools down, becomes denser, and sinks back to the bottom to start the cycle again. This is the process of convection, the slow, steady turning of a fluid as it carries heat from bottom to top. And so this outermost interior layer of the Sun is called the convection zone. The convection zone is a region of gentle, ongoing motion. It stretches from that boundary about 70% of the way out from the center, all the way up to the visible surface. The plasma here is still incredibly hot, millions of degrees at the bottom and cooling to about 10,000 degrees at the top. But it is thin enough, and the temperature difference between the bottom and the top is steep enough that the material can flow. The rising and sinking happens in enormous cells, giant columns of plasma that move at speeds we would consider slow on Earth, a few miles per second, but which are, by the standards of the Sun's interior, a kind of brisk, steady circulation. These convection cells carry energy the last part of the way to the surface, bringing the heat from the deep interior up to the place where it can finally be released into space as the sunlight we see and feel. The convection zone is the last leg of the energy's journey inside the sun, and it is a much faster journey than the long, slow crawl through the radiative zone. Light and heat can cross the convection zone in a matter of weeks or months, rather than tens of thousands of years. Compared to the radiative zone, it is a swift and lively place, though still, by any human measure, impossibly slow and patient. At the very top of the convection zone, we reach the boundary between the inside of the sun and the outside. This is the visible surface, the bright disk we see when we look at the sun through protective filters, the edge that defines the sun's apparent size in our sky. This layer has a name. It is called the photosphere, a word that simply means the sphere of light. The photosphere is not a solid surface. It is the depth at which the gas finally becomes thin enough and cool enough that light can escape freely into space without being immediately absorbed again. It is the layer from which the sunlight we see is finally released. The photosphere is very thin compared to the vast interior we have just traveled through, only a few hundred miles thick, a delicate skin on a star that is more than 800,000 miles across. Its temperature is about 10,000 degrees Fahrenheit, hot enough to vaporize any known material, but cool enough to emit visible light, the soft, golden white glow that fills our days. When you look at an image of the sun, you are seeing the photosphere, the darker edges of the disk, the slight dimming toward the rim. These are effects of looking through this thin, glowing layer at different angles. The photosphere is the sun's face, the boundary between the hidden interior and the open space beyond. And here, as we pause at the surface, it is worth repeating something we touched on earlier, because it is one of those quiet facts that settles the mind. The sun has no solid surface anywhere. There is no place to stand, no crust, no ground, no hidden rocky core buried beneath the gas. The sun is a ball of plasma all the way through, from the dense, almost solid-like core to the thin, wispy outer edges that trail off into space. When we speak of the sun's surface, we are really speaking of a convenient boundary, the layer where the gas becomes transparent enough for light to escape. But there is no sudden edge, no sharp line between sun and not sun. The gas simply grows thinner and thinner, and cooler as you move outward, fading gradually into the vast, dark space between the planets. This is a strange and beautiful idea, that the sun has no definite end, that it simply fades away like mist on a calm morning. It is a reminder that the boundaries we draw in nature are often more for our own convenience than for any real division in the world itself. The sun is a continuous thing, a single, vast entity that stretches from its burning core to the far reaches of its outer atmosphere, and everything in between is just the same material, in different states of heat and density and motion. So let us rest here for a moment, at the surface of the sun, having traveled from the core, through the slow, patient radiative zone, through the gentle, churning convection zone, to the thin, bright skin of the photosphere. We have built a simple map of the sun's interior, a picture of layers and zones and boundaries that are not walls but transitions, not edges but gradual changes in how the material behaves. The core, where the light is born, the radiative zone, where the light walks its slow, random path, the convection zone, where the plasma rises and sinks in great, quiet cycles, and the photosphere, where the light finally breaks free and begins its swift journey across space. This is the architecture of a star, a structure that has been stable and steady for 4.5 billion years and will remain so for billions more. And as you lie here in the dark, you can hold this map in your mind, not as something to memorize, but as a quiet, calming image, a vast, layered sphere of glowing gas, turning slowly in the silence of space, its layers moving and flowing in a rhythm so slow and so steady that it makes our own busy lives seem like the briefest of flickers. There is something deeply comforting in that, in the thought of such ancient, stable order, burning quietly in the dark, asking nothing, just shining, just being, just waiting for the light to make its way to us. But the sun does not end at the photosphere, at that thin, bright skin where the light finally breaks free. The visible surface is only a boundary, a place where the gas becomes thin enough to see through, and beyond it lies something just as real and just as much a part of the star. The sun has an atmosphere, a vast, extended halo of gas that stretches far out into space, far beyond the bright disk we see in the sky. And this atmosphere is not a simple, empty region. It has its own structure, its own layers, and its own quiet mysteries. Mysteries that remind us that even the most familiar things in the universe still hold questions we have not yet fully answered. We are going to drift out into that atmosphere now, moving past the visible surface into the two outer layers that surround the sun, the regions that are normally hidden in the glare of daylight, but can be seen, briefly and beautifully, during the special moments when the moon slides in front of the sun and blocks its bright face from view. The first layer above the photosphere is a thin reddish ring of gas called the chromosphere. The word comes from the ancient Greek word for color, because this layer, when it is visible, glows with a deep, rosy hue. The chromosphere is not very thick compared to the vast interior we have already traveled through. It extends only about 1,000 to 2,000 miles above the visible surface, a delicate, shimmering veil of gas that clings to the photosphere like a thin blanket of colored mist. The temperature here is actually cooler than the photosphere at its base, around 7,000 degrees Fahrenheit, but then something strange and unexpected begins to happen. As you move higher and higher through the chromosphere, the temperature starts to rise again, climbing from that cooler base up to tens of thousands of degrees at its outer edge. This is the first hint of a puzzle that we will come to in a moment, a quiet, gentle puzzle that the sun poses to anyone who studies it closely. Above the chromosphere lies the outermost layer of the sun's atmosphere, a vast, extended halo of extremely hot, extremely thin gas called the corona. The corona is not a neat, tidy sphere. It stretches far out into space, millions of miles from the visible surface, gradually fading into the emptiness between the planets. It is shaped by the sun's magnetic field into soft, flowing streamers and arches, delicate structures of glowing plasma that curve and sweep outward like the petals of an enormous, silent flower. The corona is normally invisible to us on Earth, not because it is dark, but because it is so faint compared to the blinding brightness of the photosphere below it. The light from the sun's visible surface is about 1,000,000 times brighter than the light from the corona, so the corona is completely washed out, hidden in the glare, just as the stars are hidden during the day by the bright blue of our own sky. But when the moon passes directly between the Earth and the sun, blocking the brilliant photosphere from view, the corona is revealed. During those brief moments of a total solar eclipse, when the sky darkens and the world grows quiet, a pale, pearly glow appears around the black disk of the moon. That glow is the corona, the sun's outer atmosphere, a ring of soft, white light with faint, wispy streamers stretching outward in all directions. It is one of the most beautiful and peaceful sights in all of nature, a moment of pure stillness and quiet wonder, and it is the only time when most of us can see this hidden part of our star with our own eyes. The corona is also the source of one of the most interesting and gentle puzzles in solar science, a mystery that we can state simply and calmly. The temperature of the photosphere, the visible surface of the sun, is about 10,000 degrees Fahrenheit. That is already an almost unimaginable heat, a temperature that can vaporize iron and nickel and every other metal in an instant. And yet, as you move outward from the photosphere, through the chromosphere and into the corona, the temperature does not continue to drop, as you might expect. Instead, it rises dramatically. The corona, that thin, wispy outer atmosphere millions of miles from the sun's surface, is heated to temperatures of 1 to 2 million degrees Fahrenheit, and in some places even hotter. That is hundreds of times hotter than the surface below it. This is a strange and unexpected fact, a fact that seems to go against our everyday understanding of how heat works. If you move your hand away from a campfire, the air gets cooler, not hotter. If you step back from a warm stove, the heat lessens with distance. But the sun's atmosphere does the opposite. The heat increases as you move away from the source. This is what is called the coronal heating problem, and it is one of those places in science where we can be honest and gentle and say that we do not yet have a complete, settled answer. Scientists have been studying this question for many decades, and they have developed several good ideas, several possible explanations, but no single explanation has been fully accepted as the complete answer. The leading ideas all involve the sun's magnetic field, that invisible web of forces that shapes the corona into its beautiful, flowing forms. The magnetic field stores energy, and that energy can be released into the plasma of the corona in various ways. It may be released in countless tiny bursts, small, continuous flares that heat the gas steadily over time, or it may be carried upward by waves, by oscillations in the magnetic field that travel outward from the surface and deposit their energy higher up. It is likely a combination of several different processes, working together in ways that are still being carefully studied. But the honest truth, the calm and restful truth, is that the exact mechanism is not fully settled. There is still something about the sun that we do not completely understand, and there is a quiet beauty in that, in the not knowing. It means that the universe still holds gentle mysteries for us, questions that have not yet been fully answered, and that is not a cause for alarm or frustration. It is simply a reminder that the world is deep, and that our understanding of it grows slowly, over time, like everything else in nature. Let us sit with that image for a moment, the image of the corona as a ring of soft, pale light around the darkened sun. It is a picture of extraordinary stillness, a moment when the busy, blazing star we know so well is momentarily hidden, and all that remains is a quiet, pearly glow, a halo of faint white light stretching out into the blackness of space. The streamers and arches of the corona, shaped by the magnetic field, move and shift over time, but so slowly, so gradually, that they appear almost frozen in place, a sculpture of gas and light held in perfect, silent balance. The corona is always there, wrapped around the sun, even when we cannot see it. It is there right now, on the other side of the world, a vast, hot, tenuous atmosphere that our planet is actually moving through. The Earth orbits within the outer reaches of the sun's corona, inside that extended halo of thin, million-degree gas. We are, in a very real sense, inside the atmosphere of a star, and yet we feel none of that heat, because the gas of the corona is so thin, so incredibly sparse, that its temperature means very little in terms of actual heat transfer. The particles are moving very fast, which is what temperature measures, but there are so few of them that they carry almost no heat energy. This is a subtle distinction, but a restful one. We are wrapped in the sun's outer atmosphere, and yet we are safe, protected by distance and by the thinness of the gas, drifting through the corona on our quiet, yearly orbit, unaware of the faint, hot breath of the star around us. The two outer layers, the chromosphere and the corona, complete our picture of the sun's structure. They are the final, fading edges of the star, the regions where the material of the sun gradually thins and spreads out into the solar system. There is no sharp boundary, no wall or edge where the sun officially ends and space begins. The corona simply fades, growing thinner and thinner until its particles are indistinguishable from the background of the solar wind, that steady stream of material that flows outward past all the planets. And that solar wind, which we will explore in its own time, is simply the continuation of the corona, the outermost breath of the sun reaching out to touch the farthest worlds. It is a beautiful, continuous structure, from the burning core to the faint, wispy edges of the corona, all of it part of one single, unified star. And as you lie here in the dark, you can hold this image too in your quiet mind. The sun not as a sharp, bright disk with a definite edge, but as a soft, glowing presence, fading gently into the space around it, its atmosphere extending outward like a slow, silent exhale, a breath that has been going on for billions of years and will continue for billions more. There is no hurry in it, no sharpness, no sudden edges, just a soft, gradual fading, a star dissolving gently into the dark, its outer glow reaching out to touch the planets that circle it, including this one, where you lie resting, wrapped in the quiet of the night. Now let us turn our gaze back to the visible surface, to the bright face of the sun that we have been drifting away from, and look at it more closely. The photosphere, that thin, glowing skin where the light breaks free, is not a smooth, featureless shell. It has texture, a kind of quiet, shifting pattern that plays out over days and weeks and years. If you could look at the sun through a safe telescope, one designed to filter its blinding light down to a soft, viewable glow, you would see that its surface is marked here and there by dark patches, spots that come and go and shift and fade in a slow, steady rhythm. These are sunspots, and they are one of the most ancient and most easily observed features of our star. People have been watching them for centuries, tracking their movements across the solar disk, noticing the way they grow and shrink, and follow a pattern that repeats, with quiet regularity, over the course of about 11 years. A sunspot, at its simplest, is a patch of the sun's surface that is cooler than the material around it, and because it is cooler, it glows less brightly, which makes it appear dark in contrast to the surrounding photosphere. But it is important to understand, right from the start, that the word cooler here is a relative term. A sunspot is still unimaginably hot by any earthly measure. The bright surface of the sun around a sunspot is about 10,000 degrees Fahrenheit. A typical sunspot might be around 6,500 degrees Fahrenheit. That is roughly the temperature of the hottest blast furnace ever built by human hands. It is hot enough to melt tungsten, the metal with the highest melting point of any element. It is hot enough to vaporize rock and iron and everything else we know of in an instant. So when we say a sunspot is cooler and darker, we are speaking in the gentle, relative language of the sun itself. The sunspot is only dark by comparison, a soft shadow on a face of almost unbearable brightness. If you could somehow pluck a sunspot from the sun and place it alone in the night sky, it would shine brighter than the full moon. It is only the contrast that makes it seem dark, the way a cloud passing in front of the sun can seem gray and heavy, even though the cloud itself is still bathed in brilliant light. What causes these cooler patches to form on the sun's surface? The answer lies in the sun's magnetic field, that vast, invisible web of forces that we touched on when we spoke of the corona. The sun, being a giant ball of electrically charged plasma, generates a powerful and complex magnetic field. This field is not static. It twists and shifts and tangles over time, because the sun does not rotate as a single solid body. The equator of the sun spins faster than the poles, a phenomenon called differential rotation, and this difference in speed stretches and winds up the magnetic field lines like threads being twisted around a spool. Over time, these twisted magnetic fields can become strong enough to punch through the photosphere, rising up from the interior in great looping arcs. Where a strong magnetic field loop emerges from the surface, it does something remarkable. It suppresses the flow of heat from below. Remember the convection zone, that churning layer where hot plasma rises and sinks in great slow cycles? That convection is one of the main ways that heat is carried to the surface. But a strong magnetic field can block that flow, holding the rising plasma in place and preventing fresh heat from reaching the surface. The region where the magnetic field is strongest becomes starved of new energy, and as a result, it cools down. It becomes a sunspot. A sunspot is not just a single, simple dot. Often, sunspots appear in pairs or in larger groups, and a mature sunspot has a distinct structure. The dark, central part is called the umbra, a word that means shadow, and it is the coolest, most magnetically intense part of the spot. Around the umbra is a lighter, more textured region called the penumbra, which looks like soft, wispy filaments radiating outward from the dark center. These filaments are shaped by the magnetic field lines spreading out as they leave the spot. The whole structure can be enormous. A large sunspot can be many times the diameter of the entire Earth, a vast, dark island on the face of the sun that persists for days or weeks before slowly breaking apart and fading away. Smaller sunspots may last only a few days, while the largest can endure for months, carried across the solar disk by the sun's rotation, disappearing around the far side, and then, sometimes, reappearing 2 weeks later, still holding their shape, still marking that same region of tangled magnetic field. And sunspots are not random, isolated events. They follow a pattern, a slow, steady rhythm that has been observed for more than 200 years. The number of sunspots visible on the sun rises and falls over a cycle that lasts about 11 years. At the peak of this cycle, called the solar maximum, the sun's face may be dotted with dozens or even hundreds of sunspots at any given time, great clusters of dark patches scattered across the bright disk. At the low point, called the solar minimum, the sun can go for days or weeks with no spots at all, its surface smooth and quiet and almost featureless. This 11-year cycle is not a rigid clockwork thing. Some cycles are more active than others. Some maxima have more spots, some minima have fewer. But the overall rhythm is steady, a slow, breathing pattern that the sun has been following for as long as we have been able to observe it, and almost certainly for much, much longer than that. This cycle is connected to the sun's magnetic field in a deep and fundamental way. Over the course of the 11 years, the sun's magnetic field completely reverses its polarity. The north magnetic pole becomes the south, and the south becomes the north. Then, over the next 11 years, it flips back again. So the full magnetic cycle of the sun is actually about 22 years, 2 sunspot cycles for the field to return to its original orientation. The sunspots themselves are a visible sign of this slow, grand reversal. They emerge at the beginning of a cycle at high latitudes, closer to the sun's poles, and then, as the cycle progresses, they appear closer and closer to the equator, forming a pattern that, when plotted over time, looks like a series of butterfly wings spreading across the face of the sun. This is called the butterfly diagram, and it is one of the quiet, beautiful patterns that the sun weaves for us, a visual record of its slow, steady breathing. There is something deeply restful in thinking about this cycle, this 11-year rhythm of spots appearing and fading, of the magnetic field twisting and untwisting and twisting again. The sun has its own pace, its own slow heartbeat, and it does not hurry. A single cycle, from minimum to maximum and back to minimum, spans more than a decade. A human lifetime of 80 years contains about 7 of these cycles. The sun has been breathing this way for 4.5 billion years, and it will continue to breathe this way for billions more. The spots themselves come and go, individual and temporary, but the rhythm endures, steady and reliable, a slow pulse that underlies everything else the sun does. You could think of it, as you lie here in the dark, as the sun's own quiet breathing pattern, a slow inhalation and exhalation of magnetic energy that takes a full decade to complete. Inhale, and the spots multiply. The surface grows textured and complex. The corona fills with loops and streamers. Exhale, and the spots fade. The surface smooths. The corona quiets and simplifies. Inhale, exhale, over and over, a rhythm so slow that it is almost impossible to feel from our short human perspective, but so steady that it has been going on since long before the earth was cool enough to have solid ground. And as you drift, you might imagine what it would be like to watch this cycle from a great distance, to sit in the quiet of space and observe the sun as it slowly breathes its way through the years. The spots would appear as small, dark freckles on the bright face, migrating from the poles toward the equator, growing and shrinking and clustering and dispersing. The whole surface would seem almost alive, not in a dramatic or alarming way, but in the way a calm lake is alive with ripples and reflections, always moving, always shifting, but never losing its essential stillness. The sun's skin, if we can call it that, is a skin that is always changing, always renewing itself, marked by the quiet traces of the powerful, invisible forces that churn beneath it. And yet, for all that movement, for all those shifting spots and twisting fields, the sun remains, at its core, the same steady, faithful presence it has always been. The spots are just a detail, a texture on the surface, a sign of the deep and patient processes that keep the star alive and shining. They do not threaten, they do not alarm. They are simply there, part of the sun's quiet, ongoing story, a story that continues even now, on the other side of the world, while you lie here in the peaceful dark, your own breathing slow and steady, matching, in its own small way, the slow, ancient rhythm of the star that lights our days. The sun does not simply shine and sit still. It does not just burn quietly in the center of the solar system, holding its light and its heat to itself. The sun is constantly, gently, releasing material into the space around it. It breathes outward, sending a thin, steady stream of particles flowing past every planet, every moon, every distant rock and icy body that circles it. This stream is called the solar wind, and it is one of the most far-reaching and quietly beautiful aspects of our star. The solar wind is the continuation of the corona, that hot, thin outer atmosphere we spoke of earlier. The corona is so hot, millions of degrees in places, that the particles in it are moving at incredible speeds, and because the corona fades gradually into space, with no sharp boundary to hold it in, some of those fast-moving particles simply escape. They stream outward in all directions, a constant, gentle outflow of charged material that fills the entire solar system. This is the solar wind, the quiet breath of the sun, blowing past us even now as we lie here in the dark. To understand the solar wind, we first have to understand what it is made of. The sun, as we have said, is mostly hydrogen and helium, and the corona is made of the same material, heated to extraordinary temperatures. In that heat, the hydrogen and helium atoms are stripped of their electrons, just as they are in the rest of the sun, becoming a plasma of free protons, free electrons, and other charged particles. When we say the solar wind is a stream of charged particles, we mean it is made of these tiny, electrically active pieces of atoms, flowing outward through space at speeds that range from about 250 miles per second to more than 500 miles per second. That is fast enough to cross the entire United States in about 5 seconds, fast enough to travel from the Earth to the Moon in less than an hour. And yet, for all that speed, the solar wind is incredibly thin. By the time it reaches the Earth, there are only a few particles per cubic inch, a density so low that we would call it a perfect vacuum in any laboratory on Earth. The solar wind is a presence, a constant flow, but it is a presence made of almost nothing, a breath so faint that we can only detect it with sensitive instruments and the quiet, dancing lights it paints in our polar skies. The solar wind is not perfectly steady. It varies, gently and naturally, with the rhythms of the sun. During the quiet part of the 11-year sunspot cycle, the solar minimum, the wind tends to be slower and more uniform, a steady, gentle breeze blowing outward from the sun's quieter regions. But during the more active part of the cycle, the solar maximum, the wind can become faster and more gusty. Coronal holes, which are regions of the corona that are cooler and less dense than the surrounding areas, can open up and release faster streams of solar wind. And the same magnetic activity that creates sunspots can also produce larger, more dramatic releases of material, bursts of plasma that are flung outward into space. These are called coronal mass ejections, and they are part of the broader picture of what we can gently call space weather, the changing conditions in the space around the Earth and the other planets, driven entirely by the mood and rhythm of the sun. But even at its most active, the solar wind is not something to fear. It is simply a natural part of the solar system, a feature of our environment, as normal and as steady as the rising and setting of the sun itself. And for us, here on Earth, the solar wind mostly goes unnoticed because our planet has a protective shield. Deep inside the Earth, the movement of molten iron in the core generates a magnetic field, a vast, invisible bubble that extends far out into space. This magnetic field, called the magnetosphere, acts like a kind of soft, invisible umbrella, deflecting the solar wind around the Earth and protecting the surface from the stream of charged particles. When the solar wind reaches the Earth, it does not slam directly into the atmosphere or the ground. Instead, it flows around the magnetic field, shaping it into a long, swept-back teardrop that stretches far out on the night side of the planet. The solar wind presses on the magnetosphere, compressing it on the day side and stretching it out on the night side, but it does not penetrate. We are safe inside our magnetic bubble, sheltered from the quiet, constant breath of the sun. But some of the particles from the solar wind do find their way in, slipping through gaps in the magnetic field near the north and south poles. And when they do, when those charged particles stream down into the upper atmosphere of the Earth, they create one of the most beautiful and restful sights in all of nature. They create the auroras, the northern and southern lights, the aurora borealis in the north and the aurora australis in the south are soft, glowing curtains of light that drift and shimmer in the polar skies. They appear in pale greens and soft pinks and gentle purples, colors that shift and flow like slow, silent rivers of light, moving across the dark sky in sheets and arcs and rippling waves. This is the solar wind made visible, the quiet breath of the sun transformed into a gentle, luminous dance at the edge of our world. The physics of the aurora is simple and beautiful. When the charged particles from the solar wind enter the Earth's upper atmosphere, they collide with the atoms and molecules of the air, mainly oxygen and nitrogen. These collisions transfer energy to the atmospheric particles, exciting them into a higher energy state. When those particles relax back to their normal state, they release that energy as tiny bursts of visible light. The green color, which is the most common, comes from oxygen atoms about 60 to 150 miles above the ground. The reds and purples come from oxygen higher up, and from nitrogen lower down. The shifting, flowing shapes of the aurora are caused by the changing flow of the solar wind, by the way the particles are funneled and guided by the Earth's magnetic field lines, and by the gentle, ongoing dance between the sun's breath and our planet's protective shield. It is a collaboration, a quiet, luminous conversation between the star and the planet, played out in slow motion in the cold, clear air of the polar regions. Imagine for a moment what it would be like to lie on your back in the snow of a far northern land, wrapped in warm blankets, looking up at a sky that is slowly coming alive with light. The first thing you might see is a faint, pale glow, just a suggestion of green on the northern horizon, so subtle you are not sure if it is really there. Then, slowly, very slowly, the glow brightens and spreads, forming a low arc that stretches across the sky from east to west. The arc begins to ripple, as if a gentle wind were blowing through it, and fingers of light reach upward, climbing toward the zenith. The colors shift, green to pale pink, to a soft, deep purple, and the whole curtain of light seems to sway and fold, like a vast, silent drapery, billowing in a breeze you cannot feel. There is no sound, no wind, no movement, except the slow, hypnotic dance of the light itself. The stars shine through it, faint but visible, and the whole world below is silent and still. This is the aurora, the northern lights, the quiet gift that the sun gives to our planet, a reminder that even in the coldest and darkest places, there is light and motion and beauty, delivered across 93 million miles of space by the steady, patient breath of a star. The auroras are not rare. They happen all the time, circling the magnetic poles in glowing, shifting rings. During times of higher solar activity, When the solar wind is faster and denser, the auroras grow brighter and more active, and they can sometimes be seen farther from the poles, reaching down into the skies of more temperate lands. During quiet times, they retreat poleward, becoming fainter and smaller, but they never stop entirely. The solar wind never stops blowing, and the Earth's magnetic field never stops deflecting it, and the auroras never stop glowing. They are a constant feature of our planet, a steady, beautiful phenomenon that has been occurring for billions of years, long before there were human eyes to see them, and will continue for billions of years after we are gone. There is something deeply comforting in that, in the thought of those silent rivers of light flowing and shifting in the polar skies, whether anyone is there to watch them or not. They are a permanent part of the Earth, a feature of the planet as steady as the oceans and the mountains, driven by the same quiet, patient star that rises every morning and sets every night. And the solar wind does not stop at Earth. It blows outward, past the orbit of Mars, past the asteroid belt, past the giant planets with their own magnetic fields and their own auroras. Jupiter and Saturn both have auroras, far larger and more powerful than Earth's, driven by the same solar wind and by the internal magnetic fields of those giant worlds. The solar wind blows past Uranus and Neptune, past the distant, icy bodies of the Kuiper belt, and out into the true depths of space. There is a boundary, far out beyond the planets, called the heliopause, where the solar wind finally grows so thin and so weak that it merges with the background material of the galaxy, the thin gas and dust that fills the space between the stars. That boundary, the edge of the sun's influence, is the true edge of the solar system, the place where the quiet breath of our star finally fades away into silence. And even there, at that vast distance, the particles of the solar wind are still moving, still streaming outward, carrying with them the last faint traces of the star that gave them birth. So as you lie here in the dark, with your breathing slow and your body heavy and relaxed, you can think of the solar wind flowing past the Earth, flowing past this very room, a river of charged particles so thin and so gentle that you would never know it was there. It is flowing around the Earth's magnetic field right now, streaming past the poles, lighting up the auroral ovals with their quiet, shifting glow. It is flowing past the other planets, past the spacecraft that we have sent out into the depths, carrying with it the faint, steady signature of the sun. And it has been flowing for as long as the sun has been shining, a constant, quiet outflow that is as much a part of the star as its light and its heat. The sun does not just shine on us, it touches us, gently and constantly, with its breath. It sends its material to us, a thin, warm stream of particles that wraps around our planet and drifts past us into the night. And that breath, that solar wind, is one of the quiet threads that connects us to the star we orbit, a thread of matter and energy that has been unbroken for 4.5 billion years. You are connected to the sun, right now, not just by the light that warms your days, but by the steady, silent stream of particles that flows from its corona, past the Earth, and out into the vast, quiet dark. And now, having followed the solar wind outward past the Earth and into the deep reaches of space, let us widen our view even further and look at the whole family of worlds that circle the sun. The sun does not sit alone in the vastness. It is the center of a system, the anchor of a great, slow dance of planets and moons and smaller bodies, all of them held in place by the quiet, invisible pull of the star at the center. This is the solar system, the sun's family, and it is a place of extraordinary order and stillness, a structure so stable and so ancient that it has been turning, quietly and reliably, for most of the history of the universe itself. The force that holds this family together is gravity, the same gravity that holds you gently in your bed right now, the same gravity that keeps the oceans in their basins and the atmosphere wrapped around the Earth. Gravity is the attraction that all objects with mass have for one another. The more mass something has, the stronger its gravitational pull. And the sun, as we have already learned, contains almost all of the mass in the solar system. To be more precise, The Sun makes up about 99.8% of all the mass in the entire solar system. Everything else, all the planets, all the moons, all the asteroids and comets and dust grains, everything combined, makes up only about 1/5 of the total. Jupiter, the largest of the planets, is more massive than all the other planets put together, and yet Jupiter is still less than 1,000th the mass of the Sun. The Sun is, by an overwhelming margin, the dominant object in this system, the great gravitational center around which everything else must orbit. If the solar system were a great, slow waltz, the Sun would be the still, steady point at the center of the dance floor, while the planets trace their quiet circles around it. There are 8 planets in the Sun's family, 8 major worlds that orbit the star in nearly circular paths, all moving in the same direction, all lying in roughly the same flat plane. This plane is called the ecliptic, and it is a remnant of the way the solar system formed, a story we will come to in its own time. The 4 planets closest to the Sun are the rocky terrestrial worlds: Mercury, Venus, Earth, and Mars. They are relatively small, dense, and made mostly of rock and metal, with solid surfaces that you could, in theory, stand on. Beyond Mars lies the asteroid belt, a broad, thin ring of rocky debris, leftover scraps from the formation of the planets, tumbling slowly in the space between the inner and outer worlds. Then come the 4 giant planets: Jupiter, Saturn, Uranus, and Neptune. Jupiter and Saturn are gas giants, vast spheres of hydrogen and helium, with no solid surface anywhere, not unlike the Sun itself in composition, but far, far smaller and cooler. Uranus and Neptune are ice giants, made of heavier materials like water, ammonia, and methane, frozen into a thick, slushy mantle around a rocky core. Beyond Neptune lies the Kuiper Belt, a second ring of icy debris, home to Pluto and countless other small, frozen worlds, and beyond that, the vast, spherical Oort cloud, a shell of comets that marks the very edge of the Sun's gravitational influence. Each of these planets, these 8 worlds and their many moons, follows a steady, predictable path around the Sun. The Earth, our home, completes one full orbit every 365¼ days, which is, of course, 1 year. Mercury, the closest planet to the Sun, races around its orbit in just 88 Earth days because it is so close to the Sun's gravity and has such a short path to travel. Venus takes 225 days, Mars takes about 687 days, nearly 2 Earth years, and the outer planets, far from the Sun's warmth, move with a slower, more stately pace. Jupiter takes nearly 12 Earth years to complete a single orbit. Saturn takes about 29 years. Uranus takes 84 years, a full human lifetime. And Neptune, the farthest of the planets, takes nearly 165 years. A single year on Neptune is longer than any human being has ever lived. When Neptune was first discovered in 1846, it had not yet completed even one full orbit around the Sun since its discovery until the year 2011. Think of that slow, patient pace, a world so distant and so unhurried that its year spans centuries of our time. There is something deeply restful in that image, a planet drifting so slowly along its orbit that a human lifetime is just a fraction of its year, a brief, gentle moment in its long, quiet journey around the star. And all of this motion, all of these orbits, are governed by a simple and beautiful set of rules. Rules that were worked out centuries ago by patient observers of the sky. The closer a planet is to the Sun, the faster it must move in its orbit to avoid falling inward, and the shorter its orbital path, so its year is shorter. The farther a planet is, the slower it moves, and the longer its path, so its year is longer. This is not a law that the planets chose. It is simply the natural consequence of gravity, the way objects move in the curved space around a massive body. The Sun's gravity reaches out across the entire solar system, shaping the paths of everything within it, and the planets respond by falling, endlessly and perfectly, around it. They do not slow down or speed up in any noticeable way. Their orbits are stable, almost perfectly circular, and they have been this way for billions of years. The solar system is not a chaotic, random place. It is a place of deep, quiet order, a clockwork of worlds turning in the silent dark. And at the center of it all, holding everything together, is the sun. It is the anchor, the fixed point, the steady presence that makes all of this motion possible. Without the sun's gravity, the planets would fly off into interstellar space, cold and dark and alone. Without the sun's light, they would be frozen, lifeless spheres, their surfaces locked in eternal night. The sun gives the planets their paths and their warmth, and it has been doing so, without interruption, for 4.5 billion years. Every orbit that Mercury has ever traced, every circuit that Neptune has ever made, has been guided by the quiet, invisible hand of the sun's gravity. The planets dance around the sun, and the sun, in its turn, holds them close, a parent star with its family of worlds spread out around it in a great, slow, silent spiral of motion. Let us pause for a moment and picture this scene from a great distance, from somewhere far above the flat plane of the ecliptic. Imagine you are floating in space, looking down at the solar system from a vantage point so high that you can see the whole thing at once. The sun would be a bright, golden point of light at the center, so bright that it would be hard to look at directly, its light spilling outward in all directions. Around it, the planets would be arrayed in their concentric orbits, tiny specks of reflected light, each one moving at its own pace, in its own quiet circle. Mercury, close in, would be a swift, faint dot, racing around its tight orbit. Venus, brighter and larger, would follow a slightly wider path. The Earth, a pale blue point, would be next, with the Moon a tiny, silver companion circling it. Mars, a small, reddish speck, would follow. Then the vastness of the asteroid belt, a thin scattering of dust and rock, and then Jupiter, the king of the planets, a pale, banded giant with its train of moons. Saturn, with its gorgeous rings, a delicate, luminous disk tilted slightly on its axis. Uranus, a pale blue-green dot, and Neptune, a deeper blue, the last of the planets, tracing its slow, 200-year circle around the distant sun. And beyond them, the Kuiper belt, a faint, icy ring, and the Oort cloud, a spherical haze of comets so distant and so thinly spread that it would be almost invisible, the very edge of the sun's domain. If you could watch this scene for 1,000 years, you would see the inner planets trace their swift, repetitive circles, thousands of orbits for Mercury, hundreds for the Earth, while Jupiter and Saturn make only a handful of leisurely circuits, and Neptune barely moves from its place. The whole system would turn with a quiet, steady grace, a music of the spheres made visible, a dance without a sound. There is a profound stillness in this image, a sense of peace that comes from watching something so vast and so ordered, something that asks nothing of us and needs nothing from us, something that simply is. The solar system has been turning this way since before the first life appeared on Earth, and it will continue to turn this way long after we are gone. Our own brief lives, our worries and our hopes and our small, daily struggles are set against this backdrop of cosmic order, this great, silent clockwork that measures time in orbits and epochs. And there is comfort in that, not because we are small and insignificant, but because we are part of something so stable, so enduring, so perfectly balanced. We belong to a family of worlds, held together by a star, and that star has never once failed us. As you lie here in the dark, you are on one of those worlds, the third one out from the center, the pale blue dot. It is spinning slowly beneath you, turning you away from the sun, so that you can rest in the cool, quiet shadow of its night side. The sun is still there, on the other side of the world, still shining, still holding everything in its place. And the Earth is still moving, carrying you at about 67,000 miles per hour in its orbit around the star, a speed so smooth and so constant that you feel nothing at all. You are a passenger on a planet, a traveler on a world that has been circling the sun for 4.5 billion years. And right now, in this moment, you are simply resting, letting the motion carry you, letting the quiet order of the solar system hold you in its gentle, ancient rhythm. There is nothing you need to do, nowhere you need to go. The sun has your orbit in hand, just as it has the orbit of every other world in its family. You can rest now, safe in the knowledge that the great dance continues, and you are part of it, a quiet, breathing part of the solar system, held in the steady light of a faithful star. Every story has a beginning, a quiet moment when something new first stirs and takes shape. The sun, that faithful star, that steady, ancient presence in our sky, also had a beginning. It was not always there, shining in the dark. It was born, like all stars are born, from a vast and quiet cloud of gas and dust, drifting in the space between the stars, waiting for the right moment to begin its long, slow journey toward light. And now, as we turn toward deep time, toward the distant past, I want to tell you that story, not as a dramatic tale, but as a gentle, unhurried unfolding, the way a flower opens in the morning, the way a seed stirs in the earth and slowly, patiently, begins to grow. About 4.5 billion years ago, in a part of our galaxy far from where we now sit, there was a cloud. Not a cloud like the ones in our sky, soft and white and full of water droplets, but a vast, diffuse cloud of gas and tiny grains of dust, hanging in the cold, dark space between the stars. This kind of cloud is called a nebula, a word that simply means mist or cloud, and it was immense, stretching across light years of space, made mostly of hydrogen and helium, with a thin sprinkling of heavier elements, the ashes of older stars that had lived and died long before. The cloud was cold, only a few degrees above absolute zero, and it was dark, invisible to any eye that might have been there to see it. It was quiet, drifting peacefully, its particles held apart by their own slight warmth and by the faint magnetic fields that threaded through the cloud. For a long time, nothing much happened. The cloud just hung there, patient and still, a seed waiting for the right conditions to begin its transformation. But the cloud was not perfectly uniform. There were places within it that were slightly denser than others, places where the gas and dust had gathered just a little more thickly over the eons. And in one of those denser regions, a slow, quiet process began. Gravity, that same force that holds you to your bed and holds the planets in their orbits, started to pull the material of the cloud inward. Very slowly at first, almost imperceptibly, the gas and dust began to drift as toward the center of the densest clump, drawn together by their own mutual gravitational attraction. As more material gathered, the gravitational pull grew stronger, which drew in more material, which made the pull stronger still. This is the way all stars begin, not with a sudden flash or a violent explosion, but with a slow, steady collapse, a gentle falling inward that takes millions of years to complete. As the cloud collapsed, it began to spin. This is a natural consequence of the way gravity works, a principle called the conservation of angular momentum, which is just a technical way of saying that a collapsing cloud will always start to rotate, like water spiraling down a drain, like a skater pulling their arms in and spinning faster. The cloud flattened into a spinning disk, with most of the material falling toward the center, while the rest spread out into a broad, thin plane that rotated around the central mass. This is a common shape in the universe, this disk around a central hub, and you can see it in spiral galaxies, in the rings of Saturn, and in the young solar systems that we observe scattered among the stars. At the center of this spinning disk, the material grew denser and denser, and as it grew denser, it grew hotter. This is another natural consequence of the physics involved. When you compress a gas, it heats up, and the gas at the center of this collapsing cloud was being compressed by the weight of all the material falling inward from above and around it. The temperature at the center began to rise, slowly at first, then faster and faster as the collapse continued. The central mass became a protostar, a young, growing star that was not yet hot enough or dense enough to begin the nuclear fusion that would eventually define it, but was glowing with the heat of its own formation, a dull, reddish warmth in the dark of its natal cloud. The protostar continued to gather mass, pulling in gas and dust from the surrounding disk, growing larger and hotter and denser with every passing millennium. And then, after millions of years of slow, patient gathering, the center reached a critical point. The temperature at the core hit about 27 million degrees Fahrenheit. The pressure became so immense that the hydrogen atoms could no longer resist being pushed together. And in that moment, the process of nuclear fusion began. Hydrogen nuclei, pressed together by the unimaginable weight of the material above them, began to fuse into helium, releasing tiny bursts of energy with each fusion event. The star, our sun, began to shine. It began to produce its own light, not from the heat of its collapse, but from the steady, ongoing fusion of hydrogen in its core. The sun was born. This is the moment, about 4.5 billion years ago, when the sun became a true star, a self-sustaining engine of light and heat. The inward crush of gravity, still trying to collapse the star further, was now balanced by the outward pressure of the energy released by fusion. The sun settled into a state of quiet equilibrium, a balance that it has maintained to this very day. The remaining material in the disk around the young sun, the gas and dust that had not been drawn into the central star, began to form the planets. The inner part of the disk, closer to the sun, was too hot for ices and gases to condense, so only rocky and metallic materials could solidify. These materials clumped together into larger and larger bodies, forming the terrestrial planets: Mercury, Venus, Earth, and Mars. The outer part of the disk, cooler and more distant, retained its ices and gases, forming the cores of the giant planets, which then swept up vast envelopes of hydrogen and helium to become Jupiter, Saturn, Uranus, and Neptune. The leftover scraps became the asteroids and the comets, the small, frozen bodies of the Kuiper belt and the Oort cloud. The whole process, from the initial collapse of the cloud to the formation of the planets, took somewhere around 100 million years, a span of time that seems immense to us, but which is, in the life of a star, a brief, formative childhood, the quiet morning before the long, steady day of its adulthood. And there is a beautiful, restful thought woven into this story. The sun and the planets all formed from the same cloud, the same vast nebula that collapsed in the cold dark of space 4.5 billion years ago. The atoms that make up the Earth, the atoms that make up the oceans and the mountains, the atoms that make up your body as you lie here in the dark, were once part of that same cloud. They were drifting in space, cold and dispersed, and then they were drawn together by gravity, heated and compressed and sculpted into a star and its family of worlds. Every atom of carbon in your cells, every atom of oxygen in the air you breathe, every atom of iron in your blood, was once part of the cloud that formed the sun. You are, in a very literal and physical sense, made of stardust, made of the same material that once drifted in a cold, dark nebula and then gathered itself into a star. The sun is not just a distant object in the sky. It is our sibling, our parent, our source. We are made of the same stuff, and we share a common origin, a common history that stretches back to the quiet, slow collapse of a cloud in the dark. Let that thought settle over you now, as you drift deeper into rest. The sun had a beginning, a quiet, patient beginning, and that beginning is also our beginning. We are connected to the star we orbit, not just by light and warmth and gravity, but by the very atoms of our bodies, by the shared material of a cloud that existed long before the Earth was cool enough to have an ocean, long before the first life stirred in the warm, shallow seas. The story of the sun is our story, a story of slow, patient growth, of quiet order emerging from chaos, of light being born in the deep, hidden places and then making its way, over millions of years, to shine on worlds that had not yet formed. There is no hurry in this story, no rush, no drama. It is a story told in the slow, deep rhythms of the universe, a story that unfolded over eons and will continue to unfold for eons more. And you, resting here in the dark, are a part of that story, a quiet, living chapter in the long, gentle history of a star. And just as every story has a beginning, every star, no matter how steady and faithful, will one day reach an ending. This is not a sad thought, and it is not a thought that carries any urgency or alarm. It is simply the quiet truth of the universe, the gentle, inevitable unfolding of a process that takes place over timescales so vast that our human minds can barely hold them. The sun has been shining for 4.5 billion years, and it will continue to shine, much as it does now, for several billion more. But eventually, far in the future, long after we and everything we know have faded into the deep past, the sun will begin to change. It will enter the final chapters of its long, slow life, and it will do so not with a bang or a sudden flash, but with the same quiet, patient grace with which it has done everything else. The key to understanding the sun's future lies in understanding its fuel. The sun shines, as we have learned, by fusing hydrogen into helium in its core. Every second, 600 million tons of hydrogen are converted into helium, and a small fraction of that mass is released as energy. The sun has been doing this for 4.5 billion years, and it still has plenty of hydrogen left. But it does not have an infinite supply. The core of the sun, where the fusion takes place, contains only a finite amount of hydrogen, and over time, that hydrogen is slowly being used up, replaced by a growing core of helium, the ash, so to speak, of the fusion process. Right now, the core is about 40% helium and 60% hydrogen. In about 5 billion years, the hydrogen in the core will be largely exhausted. The core will become mostly helium, and the fusion reactions that power the sun will begin to slow down and eventually stop in the very center. When that happens, the balance that has held the sun steady for so long will begin to shift. Remember that the sun has always existed in a state of equilibrium, with the inward crush of gravity balanced by the outward push of energy from fusion. When the fusion in the core slows down, that outward push weakens. Gravity, for the first time in billions of years, will begin to get the upper hand. The core will start to contract, squeezed inward by the weight of the overlying layers, and as it contracts, it will heat up. This is the same principle we saw in the sun's formation. When you compress a gas, its temperature rises. The contracting helium core will grow hotter and hotter, and that heat will radiate outward into the layers of hydrogen that surround the core. This is where the next stage of the sun's life begins. The hydrogen in a shell around the now inert helium core will become hot enough and dense enough to begin fusing. The sun will have a new source of energy, not in its center, but in a shell surrounding the center. This shell fusion will be more vigorous than the core fusion that came before it. It will pump energy outward with greater force, and that energy will push the outer layers of the sun outward. The sun will begin to swell. It will grow larger and larger, its outer envelope expanding far beyond its current boundaries. Over the course of hundreds of millions of years, the sun will transform from the steady, yellow-white star we know into a completely different kind of object. It will become a red giant. A red giant is a star that has exhausted the hydrogen in its core and has begun fusing hydrogen in a shell, or sometimes fusing helium or even heavier elements in its center. It is enormous, cool on its surface, and reddish in color. Our sun, when it reaches this stage, will swell to a size that is difficult to fully imagine. Its outer layers will expand past the orbit of Mercury, completely engulfing that small, rocky world. They will expand past the orbit of Venus, swallowing the second planet as well. Current models suggest that the sun's expansion may stop just short of Earth's orbit, or it may reach and consume the Earth as well. The exact outcome depends on details of how much mass the sun loses during its expansion, and those details are still being studied, still a matter of gentle, quiet uncertainty. But whether the Earth is engulfed or merely scorched to a cinder, the result is the same. The world we know, the blue and green planet that has been our home for all of human history, will be gone. This is not a thought to fear. It is a thought so far in the future, so unimaginably distant, that it carries no threat at all. It is simply what will happen in the fullness of time to a star like ours. The universe is vast, and time is deep, and everything within it changes, slowly and gently, over the eons. The red giant phase of the sun's life will last for perhaps 1 billion years. For all that time, the sun will be a swollen, reddish orb in the sky, many times larger than it is now, but cooler on its surface, its outer layers radiating a softer, redder light. Eventually, the helium in the core, which has been building up for billions of years, will reach a critical point. The contracting core will become so hot and so dense that the helium nuclei themselves will begin to fuse. This process, called helium fusion, combines helium nuclei into carbon and oxygen, releasing a fresh burst of energy. For a while, the sun will have a new source of power, a new phase of stability. But this phase will be shorter than the hydrogen-burning phase, and when the helium is exhausted in its turn, the sun will have no more fuel to burn. It will be at the end of its fusion life. When fusion finally ceases altogether, the sun will no longer be able to resist its own gravity. The core will contract one last time, squeezing down into an incredibly dense, incredibly hot remnant. Meanwhile, the outer layers of the sun, which will have been pushed far out during the red giant phase, will be gently puffed off into space. They will drift outward in a series of soft, glowing shells, forming a beautiful and ephemeral structure called a planetary nebula. The name is a historical accident. Planetary nebulas have nothing to do with planets. They are simply the cast-off outer layers of dying stars, glowing faintly in the light of the exposed core at their center. The Sun's planetary nebula will be visible for perhaps 10,000 years. A brief, lovely bloom of gas and dust expanding into the surrounding space, before fading away and merging with the background of the galaxy. And what will remain at the center, where the sun once burned so brightly? The exposed core, no longer fusing, no longer producing energy, but still incredibly hot, will be a small, dense object about the size of the Earth. It will be made mostly of carbon and oxygen, the final ashes of the sun's long fusion life, compressed to a density so extreme that a single teaspoon of its material would weigh several tons. This object is called a white dwarf. A white dwarf does not generate new heat. It simply radiates away the heat left over from its formation, glowing with a faint, pale light that will slowly, over billions and billions of years, fade into darkness. The white dwarf will be the final, quiet remnant of our star, a cooling ember drifting through the galaxy long after the planets are gone, long after the planetary nebula has dispersed, long after everything we know has vanished into the deep past. This is the future of the sun. It is a future so distant that it is hard to even call it a future in any human sense. 5 billion years is a span of time that dwarfs the entire history of life on Earth. The dinosaurs went extinct 65 million years ago, and that is just a little more than 1% of 5 billion years. The Earth itself is only 4.5 billion years old, roughly the same age as the sun. So the sun still has a future ahead of it that is as long as its entire past. It is only middle-aged, a star in the prime of its quiet, steady life. The changes we are speaking of, the red giant phase, the planetary nebula, the white dwarf remnant, all lie in a future so remote that they carry no weight at all on our present lives, on our quiet nights, on the gentle rhythm of our days. And yet, there is a kind of peace in knowing this future, in holding it gently in the mind as you drift towards sleep. The sun will not last forever, and nothing else will either, but that is not a cause for sadness. It is, instead, a reminder of the deep, slow rhythms of the universe, the cycles of birth and life and gentle ending that all stars follow. The sun had a beginning, and it will have an ending, and in between, it has this long, beautiful middle, this stretch of billions of years during which it shines steadily and faithfully, warming planets and growing life, and lighting the days of countless creatures who look up and wonder. We are here, now, in the middle of that story, in the quiet, warm prime of a star that is doing exactly what it is supposed to do. And the ending, when it comes, will be just as natural, just as gentle, just as much a part of the universe's great slow dance as the beginning was. So as you lie here in the dark, let this thought settle over you like a soft, heavy blanket. The sun is changing, even now, but so slowly, so imperceptibly, that we will never see it. It is using up its fuel at a steady, patient rate, moving incrementally toward a future that is billions of years away. There is no rush. There is no urgency. There is no need to hold on tightly to the present, because the present, in the life of a star, stretches across eons. The sun will be here tomorrow, and the next day, and for all the days of your life, and for all the days of your children's lives, and their children's children, for thousands of generations, for millions of years. The red giant phase is a story for another age, a distant, gentle ending that we can acknowledge without fear, a soft close to a long and faithful life. And when it comes, it will be beautiful in its own way, a last, glowing bloom of light before the quiet, cooling dark. But that is far, far away, and right now, the sun is still shining, still steady, still holding us in its warm, patient light, just as it always has. And so we have arrived at the quiet end of our journey, the soft, still place where the story gently settles and fades. We began in the dark, lying still, thinking about the one star that lights every day of our lives. And together, we have walked through what the sun is, how it shines, how its light travels, how it is structured, and how it holds us all in its steady, patient embrace. We have looked at its past, its quiet birth in a cloud of gas and dust, and we have looked at its distant future, a future so far away that it asks nothing of us but a gentle acknowledgement. Now, in these last moments before sleep takes you, I want to return to the beginning, to the simple, restful image of the sun as a steady, faithful presence in the sky, and let that image carry you down into the deepest, most peaceful rest. The sun is still there, right now, on the other side of the world. It is shining as it has always shone, a vast sphere of glowing gas, mostly hydrogen and helium, held together by its own quiet gravity. Deep in its core, at 27 million degrees Fahrenheit, hydrogen atoms are being pressed together into helium, releasing tiny bursts of energy that will take tens of thousands of years to make their way to the surface. That light, that patient, ancient light, is being born even now, light that will one day fall on a future Earth, on faces not yet born, on mornings not yet dawned. And the light that is reaching us now, the light that left the sun's surface just over 8 minutes ago, was born in the core long before the first human beings walked the earth. It is a light that carries the memory of deep time, a light that has traveled farther and waited longer than we can truly understand. And it arrives here, quiet and warm and faithful, asking nothing, just shining, just being. The sun is a star, a true star, the closest star to Earth, sitting about 93 million miles away. It is so large that 109 Earths could fit across its face, and it contains almost all of the material in the solar system, holding everything else in its gravitational embrace. It is not a fire, not a solid body, not a planet. It is a ball of plasma, gas so hot that its atoms have come apart, and it shines because of the quiet, steady fusion happening in its hidden heart. This process has been going on for 4.5 billion years, and it will continue for billions more. The sun is only middle-aged, in the prime of its long and steady life, and it has plenty of fuel left to burn, plenty of time left to shine. The light we see, the warmth we feel, is the product of an immense and patient journey. Born as high-energy gamma rays in the core, the light spends tens of thousands of years bouncing and scattering through the dense radiative zone, a slow, random walk that has no straight path and no clear destination. It then rises through the convection zone, carried upward by the slow, churning motion of hot plasma, like soup simmering on a stove, until it reaches the photosphere, the visible surface, where the temperature is about 10,000 degrees Fahrenheit. And from there it flies free, crossing the 93 million miles of space in about 8 minutes to find us here, to warm our skin and light our days, and paint the sky in soft blues and gentle golds. The light that reaches you is ancient light, patient light, light that has traveled for longer than human civilization has existed just to touch your face on a summer afternoon. That is the kind of steadiness the sun offers, a steadiness so deep and so enduring that it makes our own brief lives feel held, gently, in something larger and more lasting than ourselves. Above the visible surface, the sun fades into its outer atmosphere, the chromosphere and the corona, where the strange, gentle mystery of coronal heating still quietly puzzles those who study it. The corona stretches far out into space, a pale, pearly glow normally hidden in the glare of daylight, visible only during the fleeting stillness of a total solar eclipse, a ring of soft light around a darkened circle. And from the corona flows the solar wind, a steady stream of charged particles that blows outward past every planet, past every moon, past every distant icy body, until it reaches the very edge of the sun's influence and merges with the space between the stars. When that wind reaches Earth, it wraps around our planet's magnetic field, and at the poles, it creates the quiet, drifting curtains of the aurora, pale green and soft pink, rivers of light flowing silently across the cold, dark sky. The surface of the sun is marked by sunspots, cooler, darker patches caused by the tangle of the sun's magnetic field, and these spots rise and fall in number over a slow, steady cycle lasting about 11 years. It is the sun's own breathing pattern, a rhythm of activity and quiet that has been repeating for as long as we have been watching, and for long before. The sun holds the solar system together, keeping 8 planets in their quiet orbits, each one moving at its own pace, from swift Mercury, racing around in just 88 days, to distant Neptune, taking nearly 165 years to complete a single circuit. And all the while, the sun sits at the center, steady and still, the anchor of the dance, the quiet heart of the solar system. The sun began, 4.5 billion years ago, from a vast, cold cloud of gas and dust that slowly collapsed under its own gravity, heating up and spinning into a disk, until the center grew hot enough and dense enough to begin fusion. And the leftover material, the scraps of that ancient cloud, became the planets, became the Earth, became us. We are made of the same stuff as the sun, the same atoms that once drifted in a nebula in the dark space between the stars. And one day, far in the future, billions of years from now, the sun will use up the hydrogen in its core and swell into a red giant, a vast, cool, reddish star that will fill the inner solar system, before shedding its outer layers into a glowing planetary nebula and settling into a white dwarf, a small, dense ember that will cool slowly in the dark for the rest of time. But that is a story for another age, a distant, gentle ending that carries no urgency at all. Right now, the sun is still shining, still steady, still holding us in its warm, patient light. And you, lying here in the dark, are part of all of this. You are part of the solar system, part of the great, slow dance of planets around a star. You are made of atoms that were forged in stars that lived and died long before our sun was born. You are connected to the sun by gravity, by light, by the steady stream of the solar wind, by the simple fact that you exist here, on this small blue world, in the quiet prime of a faithful star. The sun has been with you for every day of your life, and it will be with you for every day to come. It asks nothing of you. It does not need you to remember any of the facts we have spoken of tonight. It does not need you to understand nuclear fusion, or the radiative zone, or the 11-year sunspot cycle. It just shines, and you just rest, and that is enough. So let your breathing slow even further now. Let your body sink deeper into the mattress, heavier and heavier, softer and softer. The night is quiet around you, and the sun is on the other side of the world, still burning, still shining, still holding everything in its place. There is nothing you need to do, nowhere you need to go, nothing you need to think about or solve or remember. The story of the sun is a story of patience and steadiness and quiet, enduring light. And you can let that story carry you now, like a slow, warm current, drifting you gently down into the deepest, most restful sleep. The sun will be there when you wake. It always has been, and it always will be. And in the meantime, in the quiet of this night, you can rest. You can let go. You can drift. The light is still shining, even though you cannot see it, and it will be there, waiting for you when the morning comes.